The first one is that you have a clear experimental rationale. What is the value of this research in a broader context, whether that's related to ecology or evolution or conservation biology. For some of you, we talked about this last Friday, what your rationale is. When you come into lab tomorrow to do analyses, that's a great time to like ping me like, hey, is this what you're thinking about? This is what I'm thinking about for our project. The second thing your introduction should have is a background to your project. And this is where your references come in, which is another thing I'm looking for you to have. Reference 3 to 5 peer-reviewed scientific publications. You have gone out and gotten information about the organism that you're growing. You have gone out and gotten information about freshwater or soil chemistry and how it can vary on the scales that you're looking at. Okay, you have something to back that up. And that then should lead into your experimental hypotheses. Based on this background research, I think that I'm going to see this in my experiment that I do. What are your anticipated results? And again, thinking about it in terms of a null and these alternative hypotheses that then set you up to analyze your data in a successful fashion. As long then as it's organized and well written with appropriate grammar and punctuation, it starts out, with the word introduction in bold, you will be fine for this. I have placed online several different articles to help you with writing the different portions of a research paper. I'm glad that you guys are going to take the time now to write your introduction so that you have this portion of your project done now rather than waiting to try to finish it at the end of the semester. The most difficult thing is probably going to be formatting references, and so I will have up there very clearly labeled references with some examples of how to reference and write up your references. I don't care how you reference them in your article. If you want to list them 1, 2, 3, 4, 5, that's fine. If you want to list them by first author, last name, year, that's also fine. And then have them listed alphabetically in your reference section. But how to format those references, definitely we're going to follow like the set standard style, and I'll give you some examples. The online materials have some advice for writing introductions, and then there are lots of examples from different publications for you to read. And so again, taking 30 minutes to scroll through that before you sit down to write is probably going to be pretty helpful. The other thing about finding peer-reviewed publications is that this may be research that you need to do while you're on campus on the internet here for UC. And that if you want access to the UC online library resources behind these paywalls, you have to either VPN in or be on campus. And so this is something that you might anticipate doing again in the next couple Fridays, like come in for an hour and a half and you do your analyses, and then you sit down and look for these references and kind of work on building your research paper. The introduction and the discussion is where you're going to want to use these peer-reviewed references in order to validate your findings and your hypotheses, or to say, this other group found the exact opposite what I did. I wonder why. Tell me about it in the introduction. Okay. Do you have any questions? No? Okay. And again, we'll continue to talk about, okay, now that you've started to do your research project, tomorrow we'll talk about, okay, write the introduction, now you're ready to write materials and methods. You're writing up the methods that you're using right now. And then you're going to produce these results that go in your results section, and you're going to tell me a little bit about them, again, in the context of peer-reviewed publication in the discussion. Okay. All right, it's a new unit. And again, we only have like 8 classes left for us to talk here in lecture. We have like 3 or 4 more weeks of lab, kind of 3 weeks of independent study, and at the last day of class and lab, we're gonna have you guys tell each other and me about your independent project. We have several different topics that I want to cover here in lecture, and the first one is predation. And so, of course, this is when one organism eats another as its calorie, food, and nutritional resource. We're all familiar with the amazing predation videos of different organisms catching and consuming other things that come on these wildlife documentaries. Like, it is one of the classic stories of life on Earth is predation. It is also a major natural selective force as both predators try to become more efficient predators and as prey try to elude different types of predators. And so it serves us in our evolution context too. Predation, though, is one of the major interactions between organisms on Earth, and it happens at a variety of different scales. So we'll talk about it today in a little bit of detail. First, kind of sussing out the different types and varieties of predation. We'll go back to Locke Volterra, and not only did they talk about competition, they also tried to quantify predation. Again, their predictions in terms of theory came out different than what we see in the real world. And so there are real interesting reasons why everything hasn't just been eaten by something else already. And then at the end of class today, I want us to take this kind of to an application perspective of what does a good predator look like? And this has real applications for humans as we harvest organisms around us, as we act like artificial predators on lots of different species. How do we do this in a fashion that's sustainable for us and our prey species? And so we'll talk about maximum sustainable yield and optimum sustainable yield. Okay. There's cool pictures of predation. Okay, so what is predation? Very simply, as I mentioned a moment ago, predation is when one organism consumes another living organism. Predation is the consumption of one living organism by another. And this definition of predation is going to exclude scavengers and decomposers, which we're going to talk about as their own types of resource use and predation as we move through the semester. But we're focusing on true catch and kill predators for the next couple lectures in class. And then we'll get into some of these complexities in detail as we move on. One of the things that this is going to tie to is the building and community composition, which is our next kind of big topic, is communities. And it's going to lead into those last conversations that we have about ecosystem energetics, one of these things that happens between organisms. Because the feeding relationship in predation is all about energy consumption and how an organism gets calories as well as its micronutrients for building portions of its body. And so we can define and kind of put predators in different categories in a few different ways. And so again, the resource here is food, and then depending upon what food you eat, we can divide you into a certain type of predator. So you can be an herbivore, you eat only plant matter, primary producers. You can be a carnivore, like our kingfisher here, where you eat other types of heterotrophs. Or you can be an omnivore, like we are, like bears, gorillas, orangutans, where you eat both types of products. You eat both primary producers and you eat other types of heterotrophs. We are all intimately familiar with those types of dietary types of predators. We then can expand this and kind of look at this in a different way in predation, as at what trophic level are you eating at? And so you have a food chain, you have your photosynthesizers, your primary producers, you have things that eat them then, and you have things that eat the herbivores, right, the carnivores. The primary producers are the first level of the trophic pyramid. They're producing the organic matter and the energy that the rest of the system utilizes. You're a primary consumer if you eat primary producers. You're the first thing in line. You're a secondary consumer if you're a carnivore, if you eat primary consumers. Okay? And it can go up in terms of levels. Most trophic pyramids have at most 3 to 4 trophic levels, and we'll see as we talk about ecosystem energetics that the energy peters out. Okay, and we don't have enough energy to feed really long food chains and really complex food webs because there just isn't enough efficiency in the transfer of energy from one level to another to really fuel lots of big organisms at each of these levels. But we can define you as a primary, secondary, tertiary consumer in terms of being a predator. And then the next thing, the ones that I kind of want to detail today, are the effects that a predator has on their prey. And that can put you in a different category of predator. And again, this will have impacts for both energetics as well as for how predators affect prey. Do they kill it and eat it? Do they wait a while to kill it? How long do they feed on this? That affects the prey populations. It also affects the predator. How soon do they get access to these calories? How often do they need to kill something in order to be able to utilize their resource? So there are going to be these 4 different types of predators that we're going to talk about And then we're going to say these things happen with parasites and parasitoids, and we aren't going to talk about them again until next Thursday. We'll talk about parasites and symbiosis. Okay, so the first category of predator effect on prey are true classic predators. They catch and kill their prey immediately after capture. And our lions and our wolves are classic examples of true predators. There are different ways, again, and we'll encounter this stalk, lion, wait, ambush predators, or run after and catch everything, or filter stuff out of the ocean predators. But true predators kill their prey immediately upon capture. A humpback whale sieving out and eating zooplankton and phytoplankton is a true predator because their prey immediately dies upon them interacting with it. There's different efficiencies for prey capture here, and that's going to play into our quantification of effects on predators and prey. Not every hunt that the lion or the wolf makes is successful, and they have to constantly balance then the energetics of hunting and their success rate. And cheetahs are notorious for this, in that cheetahs put on this enormous energy output in order to catch prey. If they're consistently unsuccessful, they'll starve to death in a relatively short period of time. Okay. The next class of predators are ones that we're also pretty familiar with because we like to eat them ourselves, and these are grazers. And grazers have an interesting relationship with their prey items in that they eat only a part of the prey. And so they don't usually kill their prey items. Their prey is able to regenerate and regrow. And the grazer then is most often an herbivore. But there are some types of secondary consumers. Again, these types of plankton feeders that in a population size, they're only eating a portion of the population, and the population regenerates very quickly. We think of them as grazers. The classic example, of course, are cows and antelope that, again, eat down the grass right to the root, but then the grass regrows given enough time. The grazer moves on, the grass regenerates, the grazer can come back and eat again. This happens in lots of different types of organisms. It's not just these big four-legged ungulates. It's also the little guys. The snails here are grazing on the algae. They'll graze and eat a certain amount. They'll move off into another patch. The algae will regrow in a couple days. That's a grazer as well. They don't immediately kill the prey. And there's some kind of mutually beneficial relationship lots of time between the predator and the prey item. I mean, the predator defecates and provides nutrients. It takes out competitors that really allow for fast plant growth and regeneration. That's helpful to the plant too. All right, the third type of predator based upon their effect on prey are parasites. And parasites are an interesting organisms because they feed on the host, but they don't immediately kill it. The host stays alive. And this creates all kinds of crazy, gross pictures. It makes a parasite lecture totally awesome. But we tend to have quite a revulsion to these because we don't want parasites on us. Recognizing again that there are different levels of these types of relationships, and some of them, in terms of what a parasite truly is, they are harmful to the host in the long term. The parasite organism benefits by getting food resources, and they're harmful, detrimental to the host in the long run. Usually not lethal in the short term, but if you get a high enough parasite load, this little mouse has ticks on it. This guy has worms in his eyeball. If you get a high enough parasite load, it can kill you. And again, lots of times, once you get one parasite, it affects your immune system, and you tend to get more types of parasites. You can have endoparasites, where they live internal to your body, like the worms, or you can have ectoparasites, where they are on the outside. And again, there are different relationships here, and some of these parasites will learn to move between several different types of hosts over their life cycle, again, in order to take advantage of migration and dispersal, as well as different food resources for different larval and adult stages. But they don't tend to kill the host until later in the relationship, if at all. Parasitoids are an interesting subset of parasites in that they don't kill the host immediately, but the host will eventually die. And that's not always assured in a parasite-host relationship, but the host always dies and it eventually in a parasitoid relationship. And in a parasitoid relationship, usually it's an insect, very often a wasp, but there are some ants that do this too. They lay their eggs on a host, a living host, and the eggs themselves are not terribly harmful to the host, but then when the eggs hatch, the larval insect feed on the host and kill it. Okay, so like, it's not immediately bad for you, and then it gets you. Okay. And again, not lethal immediately, indirect prey consumption by the next generation. The wasp that lays the egg doesn't actually get the food resource from this insect because the incubator for her eggs, her babies are the ones that actually do the prey consumption. In this instance, we have a caterpillar that has been infected with many, many eggs. They are on the outside of this organism, and as they hatch, then they will burrow into the body and eat the caterpillar from the inside out. And again, it's like one of those creepy but totally cool things. Okay, like it would suck if you're the caterpillar, but we are also in awe of this relationship that it exists at all.
So something would like eat that, would it kill the eggs, or would it?
Yes, yeah. So they, if a bird comes in and eats this caterpillar, the eggs will die, of course, by the stomach juices of the bird as well as the caterpillar.
Bonus catch.
Maybe, but lots of times this actually provides a slim protection because in this case, they're so obviously infected with something else that the birds tend to avoid the caterpillars.
Oh, really?
And so it's like it's good for the caterpillar, but the caterpillar's not going to make it to be a butterfly anyways.
What happened if it like molted the eggs on it?
Doesn't help.
Doesn't help.
No. And again, like the wasps and these insect relationships are such that the wasps lay their eggs in between molts, and so that their eggs have a chance to do what they need to before they could get shed. City.
Don't the caterpillars get like a lot of like the parasites like often compared to other like?
I don't think so. This relationship with this parasitoid and even parasites is really confined to these particular types of animal relationships. Everything gets a parasite. Like there's a parasite or a virus for like everything, right? But these host parasitoid relationships are very specific. And we don't see them across a broad range of the animal kingdom. I couldn't put my finger on exactly why, but they're so specific that it has to happen at just the right moment in terms of egg laying and then prey consumption in order for it to work in terms of life cycles, that it just hasn't been adapted by too many types of parasites or predators. Okay, all right. So those are the types of predators. As we move forward, we're going to be really considering grazers and true predators. And as I mentioned, we're going to leave the parasites and the parasitoids for our discussions later next week. Definitely in terms of quantifying interactions between prey and predators, these equations work best for true predators. They work to some extent for grazers, and they really fall apart again when we consider parasitoids. And again, some parasite-host relationships this works for, but it's much more was developed for and works best for true predators and grazers. We talked about Locke and Volterra and their competition coefficients and quantifying the effect of having a competitor present on your species' growth rate and carrying capacity. And Locke and Volterra both also looked at quantifying predation effects on population growth and success for both predators and prey. So rather than species 1 and species 2 today, we're going to be talking about predator populations and prey populations. And the essence of it, the take-home message, is that predation adds a mortality factor for prey. It increases their death rate. It doesn't really affect their birth rate, but it changes their death rate. And it's not just based upon their own density now, it's also based upon essentially the density and abundance of predators. The opposite is true for predators. prey items increase their birth rate. Okay? Prey items provide food, resources, nutrition to predators. And because the predator has more food, it can devote more energy to reproduction. And so it changes their birth rate, makes it more positive. The more prey, the more food resources, the more babies you can have. It modifies birth rate. The predator is still dependent upon its normal birth rate and death rate and its density dependent factors, but now it's going to have this modifier of prey population size to its birth rate. Again, when prey are low, it can actually cause negative population growth for the predator because it affects your ability to grow and reproduce and produce successful offspring. All right. We're going to look at the math behind these equations, and again, there are going to be two, and then we're going to put them together into our kind of what can happen in all these different combinations of prey and predator numbers. But the take-home effect is that because there are predators, more prey die than they would have otherwise. And because there are prey, predators can have more meat. But it depends on where you start, and it depends on the exact relationship between predators and prey. Okay, all right. In quantifying predation, we're going to look at the effect of the predator on the prey population first. So what is the effect of the predator on the prey population? Well, it causes more of them to die than if there was not a predator. And so we add a term to their growth rate of their population. The change in prey over the change in time is equal to the per capita birth rate times the number of the prey population. Okay, that's their growth rate, their additions to the population. How many babies do they have, and then how big is their population? You'll get a certain number of babies produced depending upon how big the population is. You then will have a certain number of prey that die. Okay, and the number of prey that die will be equal to the capture efficiency of the predator, which is C, times the prey population, times the predator population. The more predators there are, the bigger this number will be, the more will die of prey. The more efficient a predator is at capturing prey, the more will die. Okay. And that's what the C is for. And C is like totally variable all over the place. Okay? It could be 0.1, it could be 0.01, it can be 5. All right, it's going to be species specific. It's going to be predator-prey specific what this capture efficiency is. Notice too that the prey population affects capture efficiency. If there are a ton of prey, it's easy for the predator to find you and eat you, and this number will go up. If your prey population is low, this drops. Okay, it is hard for your predator to find you and eat you. It affects how many of you are eaten, what your prey population is, as well as how many predators there are and the capture efficiency. So the higher the prey population, the more will be born, but the more will also be captured and eaten. You will get a higher mortality as the prey population increases. The higher the predator population, the more will be captured and eaten, the higher the prey mortality. And so there's some advantage, there's a sweet spot here, right? Where like you have just enough prey that you can be growing and reproducing, but not so many prey that you attract the attention of your predators. You having low population sizes means that your growth rate is going to be low because there aren't very many of you, but it also means your predation rate is going to be low. And so again, there are trade-offs here. And that's how this can act as a natural selective force and as a regulator of population size, as a density-dependent regulator of population size for the prey. In terms of prey population, changing low prey population, high prey population, the number of prey consumed, the slope of this line is capture efficiency. And so if the slope of this line is super steep, then the predators are very efficient at finding and eating you. If the slope of this line is nearing horizontal and is very low and slow, you have a low capture efficiency for that particular predator. Okay. Then we can look at the predator from the predator point of view. And from the predator point of view, the prey has an effect of adding nutrients, which increases your birth rate. It's a bit more complex, exactly what's happening here. So let's do this. Okay. So the change in predator population over change in time will be equal to the change in bump in birth rate from consuming prey, that's B. Okay, the B here is a factor of the increase in your birth rate from being able to eat this nutritious food resource. Times your capture efficiency times the prey population size. The more prey, the more you will have to eat, the more your birth rate will go up. The better your capture efficiency, the more you will eat, the more your birth rate will go up. The better you are at transforming food into babies, the bigger B is, the more your birth rate will go up. That's also dependent upon your current population size as a predator. Okay. This term essentially is R that we looked at in our last equation, okay, the per capita growth rate. It's now dependent upon your capture efficiency, how many of your prey there are, how efficient you are at turning prey into babies. If your population is low to begin with, you're not going to catch a whole lot of prey and have a big change. If your population is high, you can be catching a lot of prey and making a lot of babies. All right, and then we're going to take, so this is your what's added to your population each generation. We're going to subtract from that your death rate. Okay, whatever your per capita death rate is, D times your current population size. The more of you there are, the more of you will die. The fewer of you there are, the fewer of you will die. The more of you will get. Okay. The more prey there are, the more you're going to capture and eat, the higher your birth rate will be. But the higher your predator population, the higher your overall mortality. And so in order to balance mortality for a predator, there has to be an increasing amount of prey items, or else your mortality factor can overcome what you can get from food. It also means that it becomes relatively, again, a fine balancing point between eating too many prey, that then the next generation doesn't have enough. And so we're going to see that the interaction here, the interplay between not being too abundant as a prey item to attract notice, not being overpopulated as a predator to where you eat too much, gives us this balance and this shifting relationship between predator and prey over time. That we can quantify these things and we have set numbers for certain interactions, but the interaction is not static, either over space or over time. Okay, increasing prey consumed will increase the number of offspring that you can have. And so more prey items, your better capture efficiency, that'll increase your birth rate and the number of offspring you can produce. Okay, we're going to see these zero growth isoclines again, just like we did for our competition interactions. And again, in looking from the prey perspective, which is always going to be our green lines here, the prey population can increase, okay, increasing prey population size, as long as they are at below a certain point. But once they have passed that kind of population size, then they will fall back towards zero. They'll be consumed faster than they're reproducing. And this particular point at which the prey population is stable, you could say, and is neither increasing or decreasing over time, happens to be equal to their per capita growth rate divided by capture efficiency. Their population growth equals zero when predator mortality, how many of them are eaten, equals their birth rate, when they're dying and being born at the same rate. That happens to happen when the prey growth rate R, in terms of it happens at a predator population size, when the prey growth rate is the predator population size equal to the prey growth rate divided by capture efficiency. The stable growth of the prey population happens when the predator population is big enough to induce mortality equal to birth rate. Below that predator population size, mortality is less than birth and the prey increase. Above that predator population size, death by predator is greater than birth rate and the prey population will decrease over time. So what is the predator population size that is perfect for a given prey species? Well, it will act as a perfect regulation of prey growth when the mortality by the predator equals the birth rate of the prey. At a predator size bigger than that, they'll eat too many prey and the prey population will decline. At a predator population less than that, the prey population will grow in abundance because less are being consumed than are being born. And again, it's an interesting thing to hold in your mind because for an individual organism, being eaten is the end, but it does not mean the end of your population. And we're definitely looking at this from a population perspective rather than an individual organism perspective. All right. All right. From the predator side then, which is going to be our orange kind of red lines, the predator population growth equals 0 when their predator mortality equals their birth rate. Okay, the same thing for our prey. Mortality equals birth, prey population, birth rate is 0. What is the prey population then that sustains equal birth and death rates? Okay. The prey population that has 0 growth for the predator is when the prey population is equal to the death rate divided by that BC term, the efficiency of transforming food into offspring times the capture efficiency for that prey. Again, it's probably the most complex type of thing that we have looked at. But the idea is that at prey populations less than this, the death rate overcomes the additive effect of consuming prey. And as the death rate is greater than birth rate, the predator population will decline. At prey populations above this, you're going to get all kinds of increases in nutrients, all kinds of offspring produced. The population of predators will increase over time. Okay, and again, this is the predator population, so it's increasing here because they're having more births than deaths. But it's dependent upon the prey population size. Okay, if you don't have enough prey, you can't fuel enough reproduction to overcome mortality. If there's lots of prey, then your population can increase. The understanding comes in that as the prey increase, you can have more predators. But as you have more predators, you'll eat more prey. You'll affect the prey population, and you can push prey population over this line. And when that happens, then your population as a predator will go down, but that then allows the prey to increase because fewer of them are being eaten. And it moves in a cycle. Totally is. And it's so great because we haven't talked about anything specific. This is just math, and it like totally explains cycles of predators and prey that we see around us. Okay? It is like, wow, there's math under the Lion King. Like, it's as simple as that. This model works great in certain systems, just like the competition models worked great in very set situations. And so we'll see again that there are these are some underlying assumptions here, like all these numbers have to be constant over time, which totally isn't true. And that we're talking about one predator eating one prey item. Like that's the only thing that happens in the environment, and that's not true. Everything eats everything else. Affects everybody else's prey capture rate and birth rate. Okay. But in essence, it explains lots of our observations in nature. And so again, by interacting these two lines, and again, we're looking at prey population increases here, and predator populations, increasing predator population along this axis. We put our 2 zero growth isoplanes on there for prey in green and then predators in red, orange. Depending upon where we are, the two interacting will affect the two populations in different ways. If we start over here with the prey is relatively low, the prey can, and the predators are also relatively low, the prey then can increase because there's not much predation. And the predator will continue to decrease because there's not a lot of prey. So at this point in time, the predator is declining, the prey is increasing. As the prey moves over and increases in abundance, then now there can be more predation. Okay, we've passed the zero growth isoplane for the predator. And so the predator will increase in abundance as the prey continues to do so. As the predator increases, we move up the predator axis, then it eats a lot of prey. And this will then move the prey down their axis. And in this case, where we have low prey but lots of predators, then we're going to have overeat. And that's going to be bad for both types of organisms. And it pops us right back where we started. Low predators, low prey numbers. Okay. What types of predator-prey do you know interact in these types of cycles? Start low, and then you get high, and then you go low again. Both predators and prey.
Wolves and rabbits.
Good. And what are the predators for these wolves and rabbits? Owls, foxes, coyotes. They show these classic examples of boom and then bust in these interacting cycles. It is the quintessential ecology predation interaction. And again, here we're kind of plotting what's happening in each of these sectors. The prey is increasing, that then allows the predator to increase. As the predator increases, then it eats too much and the prey drop down. As the prey drop down, that drags the predator behind it. Once you get low predators, though, then the prey can increase again in abundance. Okay, classic hare, lynx, bull, owl, fox, mouse interaction. The prey increases, the predator increases, and then they crash the prey, crash themselves in the process. It goes up and down, up and down, up and down. Notice that a key factor here that allows for this cycling are generational time lags. Okay, they might start out perfectly overlapping, but then the prey has to increase before the predator can. That lag then allows them to overeat, allows them to crash the prey population. And that time lag is absolutely necessary for this cycling to actually be able to happen. If it happens over and over again at the same time, the predators will eventually eat all of the prey, and then they themselves will stop and they will fail. But if there's a time lag, again, due to life cycles, due to species-specific reproduction and growth rates, then you can set up this cycling scenario. And again, it's great if you're a lynx born here. Your life is going to see lots of snowshoe hare. It sucks for you if you're born over here. You're not going to be able to eat a lot of hare. You're going to have to eat something else. Okay, cool. All right. Does this make sense? How many of you have seen this before? Maybe not in this detail. You first. Oh. Okay. This type of interaction and the mathematics here predict that we'll get mutual population regulation, that the predators will control prey numbers, and that prey numbers in turn will control predator numbers, and that there have to be some prey in order to get lots of predators. Once you get lots of predators, you will crash and reduce the prey population. They're each and of themselves density dependent in terms of nearing their own carrying capacity, and then they're density dependent on each other in terms of growth rate and mortality factor. Okay, so do we actually see that? And the interesting thing is that when we do Lockwood-Volterra interactions in the lab, it doesn't work. Unless we do other things, the predator almost always eats the prey and then itself dies. So we went to test the Lockwood-Volterra predator interactions, just like we went to test the Lockwood-Volterra competition interactions. And It didn't work. Okay, like they killed each other. They didn't coexist. It's not what we expected. Again, Gauss, who we talked about with his protist in terms of competition, did these very simplistic predator-prey interactions in the lab. And he took this one, a paramecium, and its predator, a didinium species. And so again, the predator here is this green guy. The prey increase in abundance, and then the predators come up and they eat all the prey, and then they die. If he allowed for there to be some kind of refuge where the prey could kind of hide out from these guys, he could kind of get it started. He could get it to where the prey could exist, but then because the predator couldn't find the prey, they died. Okay, then the prey went exponentially because they didn't have a predator. He didn't get the cycling of one up and down and then up and down again. He found that if he gave them a refuge, the paramecium prey, and he put in new individuals every day, one of each, he could get the cycle to work. So you had to have a place for prey to hide from predators, and you had to have immigration. You had to have something other than just birth rate adding to the population in order for him to get the true Lockable-Volterra cycles in this particular system. And it really indicated that when we look at the world and we see these cycles, that's not just the base interaction. There's also this micro heterogeneity of the environment that allows for those cycles to take place. Now, of and of themselves, they should not be able to coexist long term. One or the other should go extinct. But because there's variability over time and space and all kinds of things, we do see that we have coexistence. Just like we saw, we see coexistence and not competitive exclusion with competition. Okay. Huppaker did very similar experiments trying to kind of verify Lockable-Volterra in the lab. He worked with mice. This guy is the predator mite, the orange colored line, and this guy is the prey mite, and this guy eats that guy. This mite likes to live on oranges and fruit, and so what Huppaker found was that if he provided a whole bunch of heterogeneity in terms of a whole bunch of oranges, little hiding places on the oranges where they're covered in paper, then there were refuges from the predator that allowed the prey to exist and to bounce back from overpredation events. If you took away that stuff, then the predator mite would eat all the prey and die, just like we saw in Gauss's protist experiment. And so again, this heterogeneity is necessary for coexistence and for cycle. Also, I don't know if I can work with mice.
Find them all and count them all.
Yeah, I would just be like itchy all the time, I think. Mice. I'm like, you say they eat oranges. Will I find them on my eyelashes tomorrow? Okay. So we've got to have this heterogeneity. My last example of this Lockable-Volterra interaction comes when we have these different moths. The Indian meal moth and its predator, which is a parasitoid wasp. Both populations in nature have these natural cycles of when the moth increases in abundance and then the parasite is able to increase in abundance. What these particular researchers did was they grew the moth here without its parasite. And you see that it goes through normal cycles of increase and decrease. When they add the parasitoid, the predator here, it allows for the cycling to continue, but it regulates the overall population size of the host moth. These are log 10 scales, and you'll notice that the moth here gets up to like 1.5 when the parasite is present. It gets up to like 2.5. It gets much more abundant when the parasite is not present. And this means that predators can act as a regulator of realized niches. And that by depressing prey population numbers, it opens up niche space for another moth to be here, eating the same thing, using the same space. This moth is not at carrying capacity because of its predator. This means that there's resource available for somebody else. It allows for fundamental niches to be created. It allows for biodiversity to have a place in the environment. You're all in the Okay, cool. So the Loco-Volterra interactions predict mutual population regulation. And there are two things then that happen as the density of prey items change. And we see that predators will have a functional response to changing prey numbers, and they will have a numerical response to changing prey numbers. And we're going to focus on functional responses either at the end of class or kind of the first thing that we talk about next Tuesday. But the functional response is that the more prey there are, the more the predator eats, the more that it acts as a predator. It does its function job of eating prey. This then serves to regulate prey population sizes, just like we saw with the wasps and the moths in our last example. And again, this kind of effect on prey is a factor of the predator population size and their capture efficiency, as well as the prey population. And it predicts then this kind of linear interaction between prey and predators. The more prey there are, the more predators there can be. We're going to see that that linearity can become more sinoid and can have odd little curves and dips in it. The functional response of predators is very linearly related to prey population sizes, and we'll talk about why that is. And again, that non-linearity of the functional response of predators provides refuges to prey that sets up and allows for cycling. All right, the predator's numerical response is that an increase in consumption of prey equals increased predator reproduction. It changes the numbers of the predators because it affects their birth. Okay. And so these are kind of two different things. The predators affect the prey population by eating, and they also affect themselves by eating, which is their numerical response. And again, that's an effect of their ability to find prey, their prey population sizes, their current population size, and their efficiency at converting food into reproductive effort. But that affects their numerical response. And there are two different things then that are happening with predators as prey populations change, as their population changes, as their capture efficiency changes. And again, we're going to be very focused on functional response. How do they affect prey populations with changing prey and predator numbers? But keep in mind that there's a biological numerical response for predators as well to eating prey. And again, it's predation, so we care about predators here, and the prey just keeps. Although we'll talk about predator defenses as well. Both of these things increase and should increase as prey and predator population sizes increase. But again, we're going to see that particularly the functional response of predators is not always linear. It has this direct relationship, as you might think. All right. What I want to talk about for the rest of class, I think, is this interesting application of predation. And this idea that there is a point where a predator could not overeat a population and could eat consistently the same amount of prey items from the population year after year after year, and thus maintain a healthy growth rate for both themselves as well as the prey population. And that's the sweet spot, essentially, for a predator population. Instead of going through these cycles, what if you could find that perfect predator population size where you could just eat the same amount of prey, and again, your predation rate equaled growth rate. And so next year, growth rate would be the same. You could eat the same amount of prey items, the same amount of babies would be born. And both your populations of predator and prey would stabilize rather than going through these big cycles. And that's what we consider sustainable predation. And from a human perspective, this is what we want to do. We want to be taking and harvesting from both kind of farmed as well as wild populations at a sustainable rate, at a harvesting rate where we can take the same amount year after year after year. And the prey won't go away. They won't go extinct. We won't overeat. We won't induce a predator-prey cycle where sometimes we're doing well and sometimes we're doing poorly. This type of harvesting practice is really important for us economically and socially, more so than environmentally. In that, as humans, when we go to harvest things from the wild, if we take too many, there will not be as many the next year. And that means we'll make less money, we'll have less market, we can have less food or less medicine that's available to us as a human global population. And so we want to be sustainably harvesting and predating upon those things around us. And growth rates and population sizes and predator-prey models can tell us what that sweet spot should be for maximum sustainable yield for any given population in its particular life history. And so sustainable predation happens when we take the maximum sustainable yield, the biggest harvest of prey items that we can take from a population indefinitely. And the idea is that you want the prey population to be growing as fast as it can so that your mortality rate can be as big as it can be, okay? And that, again, we're at our zero growth isocline so that their birth rate equals death rate. And we want that to be as big a birth rate and as big a death or harvest rate as we can make it. It means that every year we can go and harvest 10,000 pounds of tuna and not worry that in next year we can only take 9,000 pounds of tuna. And essentially this maximum sustainable yield happens when the harvest amount equals our birth rate of new individuals. And this happens to happen at a prey population size that's at half of its carrying capacity. When the prey population size is at 1/2 carrying capacity, it is at the steepest part of its growth curve. Its growth rate is the fastest, which means then we can have our biggest harvest rate. So maximum sustainable yield is the biggest harvest that we can take or that a predator can eat year after year after year, and know that every year they can have the same harvest. It's when predation equals birth rate, that zero growth isocline, or divided by C. And it occurs in our theory at 1/2 carrying capacity prey size. And prey that 1/2 their carrying capacity, they're growing the fastest, they have the highest birth rate, they shall live. Okay. These two graphs show this in a bit of visual detail. We're looking at time on this axis and our prey population size here. When there's not many of them, they grow slowly. When they're near carrying capacity, their competition with each other limits their growth, and they also grow slowly. This portion in between is when they're growing the fastest, when birth rate is the highest. And so we want our population here so that next year they can make enough individuals to reach carrying capacity. And we can harvest all those individuals, and next year they'll birth just as many that we can harvest. The bottom graph here is showing population size now on the x-axis, which is this, and it is now graphing the slope of this line, their population growth, as the y. So again, notice that it's at this middle population size when population growth is the highest, the most new individuals are at. And so for any predator, this is where we want our prey population size to be, is at about 1/2 carrying capacity. Okay. What humans classically do, and like the bulls and the wolves and the foxes, is that we overeat. Okay, we over-harvest. We just take advantage of the resources that are around us. And when we harvest or eat faster than a species can reproduce, we create these crashes in prey populations. And this is an example from human history. This is the Newfoundland Atlantic cod fishery that had this vast increase due to changes in fishing technology, like fish finding and sonar technology, lots of new boats and net, and more people interested in the industry in the 1970s. And as a result, their harvest went way up, much in excess of how many new cod were being born each year, and they caused their population to crash. And it has crashed so far that in portions of the Atlantic cod industry, they have yet to rebound and actually reopen some of these banks. In the United States, this cod industry has rebounded. It never was actually this bad as it was on the coast of Canada, which is where Newfoundland is. But in this region of Canada, they still cannot fish for cod, even though they purposely closed the cod industry in the late 1990s in order to try to allow populations to rebuild. They overharvested and they drove the fish to extinction. There's probably so much predation of any new cod that are produced in this system that they cannot rebuild their population. This is another example of overfishing, which again just has these really classic examples of overharvesting in it. We're looking at one of the sport fishing companies in Key West in Florida. And we're going to look at different pictures, and they all are going to have the same board in the background. This is like a family-run business that has been in operation for a couple generations out of this location. And so people have taken pictures with the fish they caught and then put them in the local newspaper for several decades. And so this researcher went and looked at all these different pictures of fish that were caught in order to get an idea of fish populations and fish size and how it had changed in the Gulf of Mexico. So in the 1950s, one day of sport fishing would catch you a man-sized grouper. I would pee myself if I caught a fish this big. Like, oh my God, this is the best day of my life almost. Like, with hands down and without a doubt. Okay, this is amazing. The people have caught lots of super big fish. They're all happy. They're glad they spent $50 to drink beer and catch fish this day. Okay, that's 1956. By the 1980s, you could still go out from the same location and catch a lot of fish. They're dramatically smaller.
Mm-hmm.
The people are happy. They're not super smiling. They're like, I spent $80 to drink beer and I caught a lot of fish. I'm going to ship it home to me. By 2007, your day of sport fishing looks like this. You don't even want to be in the picture with the fish. One of them, you can't even eat. This looks like a shark here too, a big shark. This is a tiny little, like 2-foot shark. That's overfishing due to both the recreational and the commercial fishing industries in the Gulf of Mexico. They have literally decimated, taken to 10% or less, the populations of these really important fish, both for community complexity and food web dynamics, and then also for economic and social services. This is the type of fishing that I'm familiar with in the Gulf of Mexico, where you can go and catch fish, but they're small, and you really have to take your time to catch them. This is $120 to be on the ocean, not to catch them.
I got that. Caught the 1980s fish.
Yeah, I think it would. I can't imagine going out when there were so many fish in the reefs.
You caught one though. You caught like 10.
Yeah, exactly. And the places that I've been with the NOAA fish guys that have been fishing for decades and know where the fish are, you can catch fish of this size in this quantity today. And they don't like to tell their coordinates to anyone in the fishing industry because they'll go and outfish them. And it's those remnant populations that are going to be the source of reproduction, of birth to rebuild these populations. This is why we need fishing regulations that are not only there on the books, but then also enforced. So we don't. Yeah.
Do you think that the fish will ever get back to the humongous size?
If left alone, like if we stopped fishing,
Oh, so
they would.
not
But
likely.
we're not going to. We need fish for food. We need fish to make a variety of different products that we rely upon in all kinds of different ways. So it's very unlikely they're going to get back to that size. I think we can get back to these numbers, but I don't know if we'll get back to those size numbers. I don't think that's sustainable for us. And that's part of this type of management, is that it has to work for us as well as the fish or the gazelles or the trees that we're harvesting from. If it doesn't work for us, then we aren't going to implement and really work with the program. Okay. I want you to try sustainably fishing. Okay, and that's our activity today, our participation point. You can work with however many group members you would like. You can work by yourself if you wanted to. I think I only have like 4 worksheets, but you can work it out on your own too. And for each group, I'm going to give you a bag of fish, and you're going to try is maximum sustainable yield fishing. Like, we're gonna say you're gonna start with 40 fish, there's 40 fish in a bag, got little beads, all the beads are the same fish, even if they're different colors. So at 40 fish, maximum sustainable yield is 20 fish. So the fishermen are gonna take out 20 fish, and that should work. You should be able to take 20 fish out year after year after year. In following the directions, you're gonna find that it may or may not work. Okay, so that's what we're doing. Okay, all right, find a partner, come get a bag of fish. I realize I have not
For lab,
recounted
did you
the
work
fish in each
with
bag,
other
but
people?
I feel good
Yeah, I did.
that they're, yeah.
Was it 2 people or one?
I worked with 2 other people,
Oh.
but we kind of went in little group things. Like,
It wasn't a partner thing at all?
it was kind of a partner thing, but it was kind of also not. It was weird.
Oh.
All right, get your names on the paper, that's how you get
All right.
credit.
Can you bring your lab book tomorrow so I can take pictures of it? Because
Sure.
I just want to write the lab report.
All right. Well, it won't be due Monday. I don't think it would be because we don't have the day. We might. I'll double check. All right. Well, let's look at these thingies.
You can like send it to me, like you don't have to bring it, like just a picture.
All right. I'll send it to you in a text, I guess. All right. So I'm supposed to try and get how many fish?
Select 20.
All right. 20 fish each.
Select one group member to be observer.
All right. Do I just hand grab them or just count them out?
I mean, there's, okay, one group member to be observer, 2 members to be fishermen.
I guess I'm a 2
So I guess
fisherman.
nobody's gonna be observer, we're just,
Okay. We're just fishing.
so do you want to be a killer whale or fisherman?
You know what? I will be a whale. All right.
A killer whale,
Yeah, I'm gonna be a killer whale.
cool.
All right. So what does killer whale do?
At carrying capacity, okay, so each fisherman catches and removes 10 fish beads
Yep. So 10 of those beads.
So each
equals
fisherman
half.
takes out 10 fish.
And
Oh,
so,
yeah, definitely, even if you
so
have.
20. So we get 20 fish.
Yeah, even if you have one fisherman, the one fisherman gets to take out 20 fish then.
All right. So you just grab out 20.
It says 10 here.
Yeah, but we're supposed to have 2 fishermen.
Oh, yeah, that's true.
Having a little bit of a rough day. All
No,
right. You just count them out real quick. Go. Sneaks in and catches 2 fish.
6,
I got
7,
dinner.
9, 10, 11, 29 now.
All right, I'll help you out a little bit. All righty. 1, 2, 3, 4, 5, 6, 7, 8, 9.
And observer adds 1 fish for every fish that was left in the bag. So how many?
All right, so I'd take everything of yours but 2, I would believe. But
So you end with how many fish in the bag? You took out 20 plus 2 is 18.
Yep, we have 18 in there, so
Yeah, so you have 18 fish,
so
and then you're gonna add another 18 for a total of,
4, 5, 6, 7, 8, 9, and I'll take 9 from you.
Okay, wait, hold on.
I'm just gonna come over here and just grab you a fish.
So, okay, how many fishes were in the bag?
40 fish in the bag.
So I took out 20 and you took out 2.
Yes.
So that's like 8, yeah.
So there was
so
18 fish in
year
the
3, and then
bag.
on the back, it says,
4,
And 18 plus 18 is
oh yeah,
Yeah.
8, 9. Okay, 18 plus 18.
36.
maximum sustainable yield is.
Okay.
Yeah,
Yes.
maximum sustainable yield says, hey, take half carrying capacity and do the do.
And what is MSY? Like,
Yeah, it always overfishes.
so it's just like 1 fish? Like,
Yeah,
what?
totally. Okay, like that's the idea.
Oh, it's
over and
M,
over again.
half and a slide to each fisherman. So it's like 20 fish. Right?
Yep.
Just
Yep.
20.
Yeah, or you could get a well and
Each fisherman catches and removes 10 fish. So it's the same thing.
So now go back.
It's your handful, and I take
How much
3 fish.
actually-
1, 2, 3.
So yeah, then you get so few fish that it's a real like the whole thing. That's what they pet farmers do. So yeah, what was it? I think that works.
Okay, I just need 2 more.
2 more? Gotcha. 2 more.
And
And
then
let's see how many fishies are left in the bag. Oh, that's not a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
13. So you had 13 more.
So give me 13 fishies, please.
10, 10, 13.
Alrighty. So that means there's 26 in the bag.
So there's 13 fish left. And so we added
Another 13, so we have 26.
26. And it's still like a year 2. What was the fish at the start? Oh, I see.
All right. So we have 26 at the start of this year.
Yeah. Sorry, I'm using your pencil. It's
That's
nice.
fine. Thank
Are you
you.
carrying capacity?
I'm just gonna grab these fishies over here so they don't intermingle.
Are you at the carrying capacity for ecosystem as an inner one? She said what carrying capacity is 20, right?
You were allowed to take 20
Carrying
without.
capacity should be 40. You're taking half of it every year. Did it work?
Are
Are you there?
All I know is this is how many fish we don't have in the bag.
A lot, right?
Yep.
So you starting year 3 with 26, and you should have 40.
Yep.
So like it didn't work.
No, it didn't work because
Why not?
the killer whale is hungry.
Because the killer whale is there, and we didn't take him into account in our harvest.
Nope. And he keeps on getting hungrier every year apparently too.
Yeah, well, he's getting bigger and older, and he has to eat more.
Gotta keep on eating them fishies.
Why did we did not reach carrying capacity?
Killer whale.
But isn't it lessening?
Yeah.
Above carrying capacity, does it just?
As in
We didn't meet carrying capacity. It's under.
Yeah,
Under 40.
Yeah, it's under 40.
It's
So if
26.
you have, if
Yep,
you
that's a lot
are
under deep.
harvesting at
No.
Because the
That'll
killer
allow you to go
whale
above
keeps
carrying
eating them.
capacity with your reproductive rate. It'll come back down in a year. But the deal there is that then you're missing out of the harvest, right? You have these extra individuals that you could have harvested instead of having to.
So can you like half of fish harvested?
Each fisherman
Yeah.
catches and
And
removes.
fishing is
So
like-
20.
Oh, there's only 6 left. There's gonna be 2 left.
Right.
And
Again, like, I think that,
Yeah, there's gonna be 2 left, but there's
Oh,
26.
yeah, that's true.
Oh my gosh.
So basically we have
There's gotta be 8 fish. 2. And then there's gotta be 4. Yeah, there's 4 fish. That's not sustainable.
Yeah. Just go fast. I would see 4 fish in that year.
Yeah.
Instead of 3. So it goes to 2. Okay.
Yeah.
I think you guys have worked through it to the point
Oh,
that
there's
you
on the back.
recognize that you will
4.
overfish. These 4 and 2.
I forgot to write names.
It's fine.
And that you'll end up at a point where your harvest becomes unsustainable and kind of quickly. Like within a few
Yeah.
years, it'll like fail.
It's
Okay.
sad.
Why did it fail in this instance?
4 fish.
Like what was screwing up your harvest rate?
Eats the liquid.
Yeah, the killer
That
whale.
one eats
Okay,
the-
like we forgot to account for natural predation and mortality. We forgot to account for environmental stochasticity, the fact that some years the temperature might be off, or there might not be enough
say
prey
20
for
fish.
our consumer fish.
Not 10.
So
5 fish
what
per
would work
fisherman.
better than 10? Or what would work better than harvesting at MSY? Something
Yes.
below MSY, okay, like 8 or 7 fish. Like you could do that year after
Assault
year after
5.
year. That's what we try to do in practice. We try to do, instead of harvesting at maximum sustainable yield, we try to harvest at optimum sustainable yield, something like 30% of carrying capacity rather than 50%. And that gives us then a buffer for natural processes to take place, for there to be natural variability. And still for us to have consistent harvest.
Fish at less.
And that's what a good predator wants to do too. Is they want to be eating at a rate at which, whatever happens with the prey, there'll be consistent prey the next year.
It's not really taken into account that. That's why, right? They just eat whatever they see.
No,
Fish.
exactly. And that's again why you have these cycles. Because they don't have the consciousness to be like, hey, Fred, leave that one alone and go eat this other thing instead. They will prey switch when prey populations get really low. They have to. But they won't do that
Can only
at, and around near carrying
Fish
capacity.
like about
They won't have
7
the
instead of the 10.
to work on that kind of social level. Cool, okay. We do optimum sustainable yield here in the US. Our fishing industry happens to be very well regulated. Fishermen are highly intelligent members of their communities, and they have long recognized that they are in danger of overfishing. So even though the sport fishing industry in the Gulf of Mexico looks really bad, most other fisheries are really well maintained. And the grouper snapper in the Gulf is a case of overharvesting before we started to implement these types of regulations. What happens in fishing today in the US is that we have these fishery management councils where everybody that's involved in the industry meets together. The scientists, the politicians, the native peoples, the actual fishermen, and they all talk about harvest quotas and harvest rates and what they want the industry to look like in the future. And it works great. The difficulty is that we can implement quotas and control harvest in US national waters out to 200 nautical miles from our borders, our physical land boundaries. Beyond that, we get into international waters. And it's the law of the high seas, which is zilch. And once you get out into international waters, anybody can harvest whatever they want. And there are no international regulations about harvesting. And that can throw off then our ability to try to manage these fish populations. That's the problem with tuna fishing today. The high seas fishing industry, no country has control over quotas and regulations. We can try to set quotas and regulations at the market when the fish are brought onto the land, but they're so profitable. When these big bluefin tuna are brought in, we're talking about hundreds of thousands of dollars. No one's going to say no. You can't sell that at this market. We want the taxes too. And so there's complete overfishing in tuna industry today for those really big long-lived tuna. That makes them even more valuable and desirable.
And then we're not going to have them as big.
Yeah, we're not going to have them as big, and they aren't going to be around this long. I love to eat tuna and sushi. Like if you've had excellent tuna and sushi, you just never go back. Nothing is quite as tasty. But I try that every other time we go out for sushi, which is one thing our kids actually do, we don't have something with tuna. We try to limit our consumption to try to help this industry. And that's what you as a wise consumer can help with overharvesting, whether it's fish or other industries as well. Cool. Okay, that's my spiel for today. Tomorrow,
later?
if
No,
you
that
need
was
to be in
here.
the lab tomorrow morning, I will be there at 10:10 and McDonough 2:45. I will hopefully have all of your pots and your dirt and your